Hello my dear friends. In this video we will see few basic things about domestic electrical faults and the protective devices used to protect our electrical devices and us from these electrical faults. Let us go to the topic. Faults. What is fault? So anything which is abnormal or unwanted in the electrical circuit will be termed as fault. As simple as that. What is normal condition? If you have a circuit, the circuit should function as per the design made for it. Suppose if you have a light or a lamp circuit, when we turn on the switch, the lamp should glow, and when you turn off the switch, the lamp should go off, and with a proper brightness in the light. In case if the circuit has some electrical issues, then the functionality of the circuit may change. So what kind of faults can happen in an electrical circuit? Basically, you can see there is three different faults that could happen in an electrical circuit. There are different faults available, but these are very basic and most frequently happening type of faults. First one is short circuit. Second one is overload. Third one is earth leakage fault. Short circuit meaning when the power supply is shorted, or when the line and neutral conductor of a power supply is connected together without having any proper resistance or a load. What happens during this time? For example, you have a supply voltage of 240 volt and you insert a conductor between the line and neutral. A conductor which has the minimal resistance, for example 1 ohms, and the supply voltage is 240 voltage. As per the Ohm's law, the current equals to voltage by resistance. As I told you, the resistance is 1 ohms and the supply voltage is 240 volt. So by this you will get the current of 240 amperes. So when there is no resistance connected across the power supply, the current which is flowing between the line and neutral is very high. Either the supply may not be able to provide this, or the conductors which we have connected may not be able to sustain this, or the socket or the terminal where you make the short may not be able to sustain this current. So whichever is the weakest point in that particular circuit will blow off. Sometime it leads to electrical fire and the major disasters. Then what is overload? Overload is not that danger as short circuit, but if you leave it for a long time without noticing it, then it may damage the load or a part of a circuit. And what is earth leakage fault? Earth leakage fault are very common when the line conductor makes a physical contact with the body of the machine or the external wall or any external bodies which has a resistance, but the current flow still happens through that particular body. Usually, for example, you take a computer, desktop computer, if the desktop computer is not properly grounded. Some of you might have come across this electrical shock in the desktop computer. The reason for this is the line conductor touches the physical body or a cover of this machine, and the current start circulating in this. Though it is a metal body, mostly it will be having its own, insulating paint or something kind of things. So it does not have huge amount of current flow, but there will be a certain amount of leakage current in this. When a human comes in contact with this, the current start flowing through the human and it reaches to the ground, and the human body has its own physical resistance. So usually the leakage current won't be very high as like short circuit currents, until otherwise if the line conductor directly touches the earth conductor, until otherwise this it won't be very high. Anyhow, the leakage current also is very danger as like the short circuit current. So we need to take care of these things. Now let us go to the detailed explanation about this short circuit. You can see in this picture, this is a three-phase star-connected system where I have a three-phase conductor, and obviously the neutral point is grounded here. Now, there are different type of fault conditions are explained here. The A fault is nothing but line to ground fault. Line to ground fault. The next B is line to line fault. That means the line conductor touches the another line conductor without any resistance. Okay, so when we have this kind of fault, say the current would circulate in this path between these two phases. Okay, so when there is no resistance offered by this path, that means the huge amount of current will start circulating here. Usually, if you see it's a transformer or a motor coil, the coil will be having its own small amount of resistance. The huge amount of current which is circulating here will lead to the coil damage or the insulation damage, so that any one of this coil may damage or both of them may also damage if the protective device not open the circuit. And the next one is line to line and then to the neutral. And the next one is about all three lines shorted, dead short. And obviously when you have dead short like this, you will have more current flow, and this type of fault needs to be rectified very, very fast. Otherwise it will lead to a huge disaster. Fine. Next one, you can see here all three lines shorted and then it is also being grounded. Here also the huge amount of current will flow to the earth. Okay, so these are the basic short circuit thing. And if it is a single phase, the line and neutral may come in contact with each other and without any proper resistance. When the resistance is very less, that means the current flow will be very, very high. So because of this high current, the circuit parts are not designed for that high current, so the circuit part may get damaged. To avoid that, we are using the protective devices. So what are the protective devices usually we use for protecting the load or the circuit from this type of fault? Is generally we use a fuse or MCB. If the load is very big, then we may use a circuit breaker. Okay, so these are the devices. Let us go to a small comparison between normal condition and short circuit condition. You can see here there is one small circuit which is having a lamp which is connected with all the protective devices. The supply voltage is 240 volt AC and frequency is 50 Hz. I have a RCD which is having 30 milliampere of tripping current and 240 volt. And similarly, I have a MCB which is designed for 6 amperes, and I have a lamp here. The normal resistance of this lamp is 600 ohms, and I have one-way switch here. So when we turn on the switch and all these protective devices, the current would flow in this direction. As the arrow mark shows, the current would flow in this direction. So the simple calculation here, the load current would be 240 divided by 600 ohms. So you will get a 0 0.4 amperes. So this would be the normal condition. So when things are going fine, so this is how the circuit behaves. And now let us see what happens when during the short circuit happens. This is one possibility. Okay, this is one possibility of the short circuit. Here what happens is the line current flows through the RCD, MCB and the switch, and between the switch and the lamp there is a short circuit between the line and neutral. So when there is a short between the line and neutral, so what happens? The resistance provided for this in the circuit is almost become zero, since the conductor doesn't have much resistance as like the lamp. So it is the resistance becomes zero. In the same equation you can see IL load current we can calculate 240 divided by 0 ohms. So anything divided by 0 is almost infinite. Practically it is very high current, and theoretically you can say infinite current. So when the infinite amount of current is passing, or the very high amount of current is passing, so the weakest part in this circuit should be open. So here we have the MCB. Okay, so usually how they design this, how they design the MCB. So the MCB or the fuse should be the weakest point in the circuit. So it should open first. Okay, it should open first, and then we will have the conductors, and then we will have a load. Okay, so usually what they do, they will see what is the load current, and then they will multiply with 1.5 times to obtain this. It's a thumb rule to obtain the MCB or a fuse, and then more than that they will have the rating for the conductors, and then the load would be the last one. So this is how they design this wirings. So usually compared to the conductor and load, we must be having the less current rating for the MCB. So the MCB will open the circuit during this short circuit. And since the current is very high here, the MCB has to open very fast. Usually the norm says the MCB must open within 100 milliseconds. 100 milliseconds, or you can say it is only 0.1 seconds during short circuit. So it is the maximum time it should take. Okay, so if it is tripping before than this, say for example you have only 30 milliseconds or 40 milliseconds of time if the MCB is opening, that means that is very good for the circuit. So the maximum time which the circuit breaker can take for tripping during the short circuit could be 100 milliseconds. So now let us go to the next one. So with next condition, so our next fault is overload. So overload is nothing but when the designed circuit is consuming more than the rated current which it's supposed to take. So the overload can be for the conductors, the overload can be for the switches, the overload can be for the load itself. Okay, say for example you have a motor or heater coil kind of things, and you are using a 1.5 mm square wire for this, and the 1.5 mm square wire which will not sustain the current which is taken by the load. So the load is maybe taking the enough correct amount of current, but the conductor size which we have chosen may be the smaller size, so conductor will heat it up and then it will fail, the insulation will fail. So this is also a kind of overload only. So the overload can be happening for the switches. If you take a small amount of current rating for the switch, it would what happens, it would heat up, the temperature of the contacts will increase, and when we are closing and opening, the sparks can be produced, and then black carbon can be produced during this. So the current rating for the load, how much is the current rating, so accordingly we have to choose the current rating for the conductor and everything. If you are not choosing the proper conductor size and the switches, then the overload can happen for the conductor as well as for the switches. On the other hand, sometimes the load itself, say for example, you have a motor which can give a particular amount of torque, but you connect a bigger load, and then the motor tries to do that work, out of its capability. So that means it will try to take more amount of current from the source. So during this time, the current may not be very high like a short circuit current, but what happens, the current would be greater than the rated current. Say for example, you have a rated current of 10 amperes for the motor, and you have connected the load which would need almost 12 to 15 amperes of current. Okay, so what happens, this will be called as a short circuit condition. So simple example for this, if you take a lift. So in the lift they will write how much capacity is there, 25 members or particular amount of kgs they will mention. But if we are crossing the limit, say if it is a 10 members can be accommodated in the lift, and say for example 13 to 14 members are standing on the lift, and the lift is trying to pull the load in the upward direction or the downward direction, what happens, the motor try to do the work, okay, but beyond its capability, so that it takes more amount of current. So it can be a short duration or it can be a long duration. If it is for long duration, then obviously it is going to affect the load, and it is going to affect the electrical circuitries. So during this time also we have the protective device, same protective device, fuse or MCB. But the reaction time for this type of fault, the MCB or the fuse will take a little more time, because it should not be turning up for the surge current. Like motor, when you are turning on the motor, the starting current would be high. So the MCB or this fuse should not blow during this time. Okay, but if it sustains for a little amount of time period, then obviously it has to open the circuit. Okay, so the mechanism which we follow for overload is different from the mechanism which is used for short circuit condition. So there are two mechanisms inside the MCB. So the different mechanism detects the fault current, and then respectively the mechanism works. Usually for overload, we have a thermal mechanism which will be slower in nature based upon the amount of current, exceeding current. Okay, and for short circuit, we have a magnetic coil or a trip coil, so which would be very fast, because the current during short circuit will be very high and it has to react very fast, right? So this is about overload condition. So you can see here, I just put a picture to explain this. So in this circuit, you can see, as usual, I said I have a RCD with the same 30 milliampere current rating, 240 volt, and 6 ampere MCB is placed here. I have three loads which is having a different current rating, and initially I turn on only one load which is taking 3 amperes of current. So now the load current is very much lesser than the MCB rating here. So obviously the system functions properly. And if you choose any one of this load, say second load is 2.5 amperes, no issues with that. If you choose the third load, it is 4 amperes, no issues with that, it can sustain. But when it comes as a combination, so say for example, if it is a 3 ampere plus 4 ampere, then what would happen? So 7 amperes of current will come, which is greater than the rated current here. So now we can see here the second combination. So the first load is consuming 3 amperes and the second load is consuming 4 amperes. Obviously this is a overload condition. So this immediately whether the MCB will trip for this? No, because this is a very very minimal amount of current is exceeding the limit. So 1 ampere only is more than the rated current, but obviously it will trip, but it will take a long time. Maybe based upon the characteristics of the MCB, it would take the time to trip. Either it is a B type MCB or C type MCB or D type MCB. So based on the sensitivity of the particular MCB, it would take a time. But if you compare to the short circuit, it would take definitely it will take a more time than that. And suppose instead of 3 and 4 amperes, if you take this load, the third load is consuming not 4 ampere. If it is, say, the third load consumes 10 amperes of current, it is not, we will not design like this, but just for explanation I tell you. So 10 amperes of current, and then your first load is consuming 3 amperes, so the total current is 13 amperes. So the first scenario we had only 7 amperes, and the second scenario we have 13 amperes of current. So here the MCB will trip slower for this 7 ampere compared to 13 ampere. So what I am trying to say is the current, the load current, which is increasing beyond the limit of that MCB. So when it is increasing, the trip time will decrease. So it is inversely proportional. So when the load current is exceeding the limit, and when it is crossing the limit of that MCB, if it is goes in the increasing mode, and then the time will be coming in a decreasing mode, or in the vice versa case. If the load, if the fault current or the load current is very high, that means the tripping time will be less. So if it goes like this, say for example, if I have a B type MCB, and this is a 6 ampere, so the trip time, trip curve will be like this: 18 amperes to uh, 18 amperes to 30 amperes. So this is the range for the overload conditions. Overload conditions. So until 30 amperes for this device, until 30 amperes, we can say it is in the overload condition. If the current goes more than 30 amperes, say for example, if the fault current goes 35 amperes or 40 amperes, like that, so that will become a short circuit. So how we classify the short circuit fault and the overload fault? It is based on the type of MCB and the trip range of the MCB. So the trip range for this is a B. If I have taken this as a B type MCB, and the IN, the normal operating current, is 6 ampere. So the trip range is 18 ampere to 30 amperes. So when until the 30 ampere limit comes, then the MCB is acting like it is a overload condition. But when it is crossing 30 ampere, if it is 35, 40, 45, anything beyond 30 amperes will be considered as a short circuit, or the instantaneous tripping time. Okay, if it crosses 31 amperes, so that means it has to trip within the 100 milliseconds time period. So if it is 25 amperes, maybe it will take little more time because it is in the overload condition. But if it is beyond this 31 amperes, then that means it will consider as a short circuit, and the trip time will be very low. It will be under the 0.1 milliamperes. So this is for MCB. Like, so the same thing, the overload condition. So if you see in this case, you have a 3 ampere, 2.5 and 4 amperes. All the three loads are connected. So the summation of the three currents here, it will be 9.5 amperes. The 9.5 ampere is absolutely, it is a overload condition. So this 9.5 ampere is very much greater than 6 amperes. So the MCB will trip. Okay, the MCB will trip, but it will take time. If it is a B6, so you have, if it is a B6 type, so until 30 amperes it is overload condition. So slowly for 10 amperes, if it is taking say for example 20 seconds, then for 20 amperes it would take 10 seconds, like that. So the time will keep decreasing, and when it is coming to 30 or more than that, it will come to 0.1 or 0.1, less than 0.1. So this is about the overload condition versus the normal load conditions. So miniature circuit breaker. So we are talking about this device which will trip during the fault, either short circuit and overload fault. So now what is this miniature circuit breaker? What is there inside this? So the miniature circuit breakers are the protective device used to protect the electrical circuit or the load from overload fault and a short circuit fault. So as I defined you little earlier, short circuit is a scenario where the line and neutral conductors are make contact each other without any proper resistance or a proper load, so that huge amount of current flow takes place during this time. It has to open the circuit very fast. So the mechanism or a material which we use inside the MCBs are magnetic stripping mechanism. So which is nothing but a simple magnetic coil. So the coil would produce a magnetic field, and the magnetic field will attract the plunger, so that the moving contact will open from the fixed contact. So the electrical contact will be opened up. And for overload condition, so whenever the load current exceeds the rated current, then obviously the thermal mechanism, so which is nothing but a bimetallic strip inside the miniature circuit breaker. So this bimetallic strip, the temperature would rise. So because of the temperature rise, and the thermal coefficient of this device, bimetallic strip, is different from each other. The two different metals will have a two different thermal coefficients, so that it would melt and then it will bend or deform. So this bending or deformation would also move the plunger, and then it will open the circuit, and then so that the moving contact and fixed contact will be moved from each other, so that the electrical contact will be removed, or the circuit will be isolated from the faulty condition. Right. So what are the specifications for this MCB? So usually we have these three terminology which we use: IN, ICN, and IPF. So IN, so which will be mentioned on any MCB, okay, so which is nothing but a normal operating current. So if I say B6 or C10 or D20, so that means the 20 is nothing but a IN. So if I say I have a D30 MCB, so this 30 meaning it is a normal operating current, and this is a type. Okay, this is a type D type, and the normal operating current is 30 amperes. Okay, so this 30 amperes, if the load current exceeds this 30 ampere of current, then it would consider as a overload condition, and then it will trip. Say for this D30, the trip range will be from 300 amperes to 600 amperes. So this is the trip range for this D30 MCB. So from 30 amperes onwards, it would say that the trip time would start, but the trip range for this is from 300 to 600 amperes. The overload condition will be considered from the 30 ampere onwards. Until 30 to 600 amperes, it would say as a overload condition. So if the load current goes beyond this 600 ampere, then it will consider as a short circuit condition. So 30 to 600. So in this range, so you will say that the circuit is in overloaded condition. So if you want to know how I am calculating these numbers, you can refer to the another video which I have posted in the same topic. You can refer in the channel. So this is about the IN. So the IN is nothing but the current which can safely pass through the MCB without tripping. Okay, either due to overload or short circuit, there is no tripping. So the safe operating current, or the safe current which can pass through this device without tripping, is called as normal operating current. And the next one is ICN or ICU. So this ICN is nothing but a prospective short circuit current capacity. So as I told you in the previous cases, here during the short circuit, if you see here during short circuit, okay, I have a 240 volt AC, and then the resistance here. If, for example, I consider all the resistance offered by the RCD, MCB, switch, and this conductor all together. For example, I have 1 ohms of resistance here. Okay, 1 ohms of resistance. So the short circuit current would be 240 volt divided by 1 ohms. So now the IPF, or the short circuit current, IPF. Okay, for this condition, IPF is 240 equal divided by 1 ohms, so 240 amperes. So this is a short circuit current, what I am obtaining for this particular source and the given scenario. So this 240 amperes is a short circuit current. So this MCB, how much short circuit current it can withstand? So in this source condition, we get only 240 amperes of short circuit current. But what is the capacity it can handle? So that is ICN. So usually the ICN is given for most of the MCB, single phase MCBs, it would be greater than 9 kilo amperes. Either it may be 10 kilo amperes or something like that. Or if it is a double pole MCB for single phase, you may see here 6000 ampere or 6 kilo amperes as a ICN value. Okay, so this why I'm trying to say this, compare this to the ICN and IPF, it is very much linked. So IPF is the actual short circuit current. You can see here we have defined the source and we have defined the resistance, and we have seen the prospective short circuit current for this particular circuit. It's a 240 amperes, but how much the MCB can withstand short circuit current is up to 9 kilo amperes. 9 kilo ampere. Say if instead of this 1 ohms, say if you have only 0.1 ohms of resistance, altogether you have only 0.1 ohms of resistance. So what would happen to the IPF? So IPF, it will multiply by 10 times. So what happens now? So 240 divided by 0.1. So what happens now? It become 2400 amperes of short circuit current. Still, this is again a prospective short circuit current. The current is still under the rated value. So the 9 kilo amperes is the capacity for this MCB, but the actual short circuit current, how much it flow through here, is only 2400 amperes. So that means the MCB will trip or will isolate this short circuit current safely without having any physical damage to the MCB. Understand? If this IPF, if the IPF goes beyond this, so if you take a 0.01 resistance, 0.01 ohms of resistance, so what would happen now? 2400 will become 24,000 amperes. Okay, so 24,000 amperes. So in this case, what happens now? 24,000 amperes is greater than 9 kilo amperes. So now the MCB cannot sustain. It will damage. Okay, it will burnt out or it will damage. It will trip, but it will damage also. Okay, so this damage could leads to physical damage. It can leads to again dead shot, so it may leads to the total circuit also in a trouble. Okay, so this is the difference. So IPF can be like 240 2400 or 2400 24,000 amperes as well, but ICN is the standard value given by the manufacturer, how much short circuit current this particular device can withstand. Okay, usually for single phase, this much big amount of short circuit current won't happen, but for example, I just tell you. So if you consider 1 ohms, you get 240 amperes. If you consider 0.1, you get 2400 amperes of fault current, and if you consider 0.01 amperes, then that means you get a 24,000 amperes. So these two fault current can be safely isolated from this MCB, but the third condition, 24,000 amperes, it cannot safely disconnect because the ICN value is only 9 kilo amperes. So this is the difference between ICN and IPF. So ICN is a capacity given by the manufacturer, how much the short circuit current this can be handled by the MCB, and IPF is the actual short circuit current. It could be 20 amperes or it could be 2000 amperes or it could be 24,000 amperes. So it can be anything, so we cannot predict. So it is based upon the circuit, and it is based upon the power source, and it is based upon the type of fault which is happened. So the IPF can be different, but ICN is the fixed one for any given particular MCB. Okay, so these are the specifications of the MCB. So IN, normal operating current, ICN, prospective short circuit current capacity given by the manufacturer. IPF is an instantaneous fault current, which would be different from each and every different type of fault. Okay, right. So now, classifications, we have different classifications available for MCBs. So I have already put one video for these types of MCB in the same channel. Please refer to that, and I have explained you the different type of MCBs and which type MCB is used for what type of load and why it is used, what is the sensitivity of this, everything. So there we have, I just put here three different type, B type, C type and D type. So B type, the trip range is given 3 to 5 IN, and C type 5 to 10 IN, and D type 10 IN to 20 IN, and the respective in applications for this. Right. So we have the protective device MCB, so which would protect us from the short circuit and from the overload. Now, in the circuit, which I have shown you a little earlier, also one more protective device I have shown, that is a RCD. Why we need that RCD? Now already we have this fuse or a MCB which can protect the circuit or load from the short circuit fault or overload fault. Then why I need the RCD? So I have given you a picture here. You can see the 220 volt supply is connected with the fuse and to the load. Okay. Fortunately or unfortunately, what happens? This human who is working in this machine touched the live conductor here. He touched the live conductor here. So when he touched the live conductor, say for example, this load is having, for example, you have 100 ohms of resistance when it is normally operating. So now the normal operating current, I can say now 220 supply voltage divided by the resistance 100 ohms. So I would get 2.2 amperes of current. And the MCB rating, you can take multiply this one with 1.5 times, you may get around 3.6. So I say that I have taken 6 amperes of fuse for this. Okay, 6 ampere of fuse. And now this human being who touched this equipment, because of this live contact from the human to the line conductor, the current start flowing in this part as well. Okay, in this part also the current is start flowing, and then it is going to the ground. Usually the resistance offered by this human being is not going to be very small, it is going to be high. Okay, so this human, say for example, he has the body resistance of 1000 ohms. It would be different for a different human being and different conditions, whether he is wet or dry, what sort of insulation he has in the hands, and then what sort of insulation or the protective shoes or whatever what he is wearing, and what kind of floor he is standing. Based on that, the total the resistance will change. For example, I have taken this human body is having 1000 ohms of resistance, and now the current which which is going through the this human body. So there is a 100 ohms resistance here, which is less resistance. Obviously, you can say this is like a parallel circuit. So one circuit or one load is having only 100 ohms, and the another load is having a 1000 ohms of resistance. So this is 1001 kilo ohms, and you have a 0.1 kilo ohm resistance here. So now the total current which is coming from here will flow through both of this network or both of these branches. So based on the resistance, the current would change, but the current will be flowing in both the directions. Then by seeing this, you know that suppose if it is a 0.1 amperes of current is flowing here, say 2.2 amperes of current is flowing here, it is 10 times greater, the resistance is 10 times greater, so obviously the current would be 10 times lesser. So say for example you get something near to 0.2 amperes. I am not going for the actual calculations, I am just assuming that 0.2 amperes of current is flowing in the human body, and it is going to the ground. Now the total summation of the current, so the load is taking 2.2 amperes of current, and then we have the human body, and the current which is flowing here is 0.2 amperes. So the total current based on the Kirchhoff law, the total current is 2.4 amperes, 2.2 plus 2.0.2, so 2.4 amperes of current is flowing through this. Now this 2.4 amperes of current, if you see, this is very much lesser than the rated current of this fuse. You will agree this, because there is a 6 amperes fuse rating or MCB rating, and the fault current, including the fault current, how much current it is drawing, it is only 2.4 amperes. Now, can you neglect this condition? Only 0.2 amperes of current is passing through this human body, so it does not affect the circuit. It does not affect the circuit, or it does not affect the switch, or it does not affect anything in the circuit. But this 0.2 amperes of current which is flowing through the human body, if it sustains for 1 second or more than 1 second, it would even kill the human. Okay, because the 0.3 milliamperes of current itself, the human being feel the shock. If the current exceeds 0.3 milliamperes of current, the human feel the shock. So when the current increases, the amount of severity also increases. So this 0.2 amperes of current or 200 milliamperes of current, if it sustains for, you know, 1 second or more than 1 second, then even it can kill the human being. So what I am trying to explain here, by having a fuse or a MCB, we cannot sense or we cannot detect this leakage current, either it is going to the human body or it is going through any physical body to the ground. So we cannot identify this, and we cannot rectify this. So the fuse is not going to identify this leakage current, and it is not going to give any protection against this leakage current. So we must have some device which can detect this, leakage current, which is a small amount of current, but it is very much lethal to the live person or a live objects. So we need to find out the leakage current. So for that we need to go for a next protective device, which is nothing but a RCD, residual current devices. So these type of fault between the line to earth. Okay, so I told you in the short circuit, line to neutral. Here now it is line to earth. So line to earth, it can happen either the line current, say if I have line wire and neutral wire, say for example, okay, so this is line conductor and I have a neutral conductor and I have a earth conductor. If this line conductor is directly shorted with this earth, and this earth is being grounded or earthed like this, what would happen? The current which is flowing in the line will transfer in the earth conductor and it will go to the ground. So it is a dead short, actually, line to earth short, okay, or line to ground fault. Here more amount of current would flow, huge amount of current would flow. If you are not using the RCD, in this case, if you are not using the RCD, the MCB will trip, because the line to earth, the resistance, the earth resistance here may be 0.1 ohms, earth conductor resistance, and line conductor resistance, let me assume 0.1 ohms, and the earth pit resistance or ZE, consider that is 5 to 10 ohms. Okay, so even if you consider 50 ohms, so altogether it is coming near to 50 ohms only. 50 ohms, and if you ideally speaking, you should not have no very high resistance for the ground. So if I take 5 ohms, 5 plus 0.1 and 0.2, so 240 divided by 240 divided by, say for example, 5 ohms. So what happens? I may get around yeah, 48 amperes. Yes, 48 amperes. Okay. Okay, so this 48 amperes is enough to trip the MCB. Okay, since it is a line to earth direct fault, the 48 amperes, say ideally speaking, now if you have the same 6 ampere MCB like what the previous discussion, so this 6 ampere MCB would trip for this 48 amperes and it would consider only as a short circuit fault. Okay, line to earth fault, huge amount of current is flowing through this. And the other scenario, if you take the another scenario where the line is the line conductor and say this is neutral conductor and then the earth conductor, you have a equipment here, and this equipment, which is say for example you have a coil here and then it is written back to the neutral line, neutral and earth. So this is the earth. Okay, the body of the machine is being grounded. So now there is a leakage like this, there is a leakage and the current starts circulating in this body. Okay, since we have grounded it properly, the leakage current which is circulating here would try to flow through this earth conductor and it will reach to the earth. So in this case, what happens actually, the resistance offered by this body, the metallic body and the conductor would be more, not like this small resistance, it would be more. Say for example, you have 50 ohms of resistance in this case, 50 ohms of resistance. And the calculation if you do 240 divided by 50, so you may get only 4.8 amperes of current. So now you see the fault current is not greater than the rated current of this MCB or a fuse. So in this case, obviously it is not going to trip. Or if you consider that the line conductor is touched by the human, okay, so this is a line and neutral, and the human being comes in contact, and then the leakage current is passing through. Suppose if this is a person who is touching the line conductor and the current is flowing through him and to the ground. So now the current path for the leakage current provided, say this is this person has 5000 ohms resistance. Okay, so certain amount of current would pass through him, but if you take this is a 240 volt and let me take this as a 2400, so for easy calculation 2400 ohms resistance. So now 240 divided by the resistance 2400 ohms resistance, so you would have only 0.1 amperes. So this 0.1 amperes is not going to be simple and it is very less current. The MCB cannot detect this 0.1 amperes of leakage current, but this 0.1 ampere current which is flowing to the human body, if it sustains for a certain duration, surely it will have a major implication on that particular human. So we need to detect this small leakage current, or we need to detect this line to ground fault, direct fault. So this kind of fault is called as direct fault, where the line and the earth conductor is directly connected and a huge amount of current flows to the earth. So this is called a direct fault. And these two scenarios will be considered as an indirect fault. Either the human makes a contact and then the body resistance sustain the current flow and then it goes to the earth, or the current flows to the body or a wall of the installation, then it goes to the ground which will have a high resistance, and but still there is a leakage current. That time we will consider as an indirect contact. So the leakage fault can be takes place either it is through direct contact or indirect contact. In both cases we should detect this fault and we should isolate. In sometimes if you are having a a good MCB, for direct fault it can trip. Okay, if you don't have RCD also, if you have a proper earthing conductor, if the proper earthing is done, the MCB can trip for the direct contact. But for indirect contact, even though your earthing is good, okay, even though your earthing is good, mostly for indirect contact you will not see that MCB is going to trip. But when you connect both of them in a circuit, surely the RCD is going to trip first. I'll tell you the reason why. So if you see how the RCD is going to detect this fault and how it is going to work. So internally the RCD has these components. So the supply coming from the phase here is going to be given in the terminals in the RCD. So we have two terminals for line and two terminals for neutral. So line input for single phase, the line input and the line output, and similarly here we have a neutral input and a neutral output. So the current is going to flow through these terminals and it will go inside. If you see, the line conductor is connected to a coil which is wound on a core, and then it goes to the external circuit. Okay, from here it is going to the external circuit. So here you will have this is my line input, the line output will be here. Okay, and similarly the neutral output would be here. The switch, we cannot see the switch, it is going to be inside. Okay, so this is not line output. So then line is given input here and neutral input here, the line output and neutral output is going to be here. So when the current is start flowing in this circuit and the load is consuming some current, so here say for example I have a load here, and then it is connected to the neutral. So when all the circuitry is connected and power supply is given, the current would start flowing in this line conductor, and then it is a coil. Okay, so there is a coil inside this RCD. The current would flow here and it will create certain amount of flux here. Okay, and then say for example this is phi L, okay, line flux, and the current is flowing to the load and the load is doing certain job, and then the return current is coming back in this coil in the neutral. So in the neutral also there is a coil which is of identical to the coil which we placed here in the line. So this also is going to produce certain flux, because whenever there is a current flow in the coil, then there is going to be a flux. So this flux, let us take this one phi neutral. Okay, so phi L and phi N is going to be equal. Phi L equals to phi N in magnitude, but the polarity wise it is going to be in opposite direction. Okay, since the current flow is in opposite direction, so the flux which is produced here is also going to be in opposite direction. So it is equal in magnitude in normal condition and it is in opposite direction. So these two flux is going to nullify the difference flux pi L minus pi N is equals to 0. Okay, since these two are equal and opposite, so the net resultant flux is going to be 0, so that there is no current which will be flowing in the sensing coil in the normal condition. Okay, so this is a normal condition. So where I have a switch connected here. Okay, so okay, so that is the normal condition which I have discussed about. It's a normal condition. Okay, so when is the fault condition? So this is normal condition where my flux which is produced in the coil placed in the line and the neutral is equal and opposite, so it nullify each other. So the sensing coil does not have any flux or the current flow, so the relay is going to be in off condition, so the line and the neutral is going to be in closed condition. The current flow takes place in a regular way. So now in a fault condition, what happens? Here the circuit is closed and the current is start flowing. Here it produces certain amount of flux. So as usual, what we have taken before, same thing will take pi L. And then the current is flowing back, but the current is not returning back in this neutral coil. Now the current goes to the ground directly. So here no current is coming. So that means phi neutral is almost equal to 0. Okay, so now the difference between the phi L and phi neutral is having certain value. Okay, so it is equal to phi L itself. So this value, this phi L flux here would start circulating the current here. So this current would flow in this sensing coil, and the sensing coil will get the electrical current here, the potential. So what happens? the sensing coil will get magnetized here. So because of this magnetization, so the switches will open. Okay, so though here it is not shown in a proper way, but it will push. Okay, it will push so that the contacts will open. Understand? So this is how the RCD works. So basic, what is the basic here? The MCB is comparing the rated current and the line current. So when there is a discrepancy between that, when the line load current is exceeding the rated current, the MCB will open. Here, it is not looking the line current, it is not looking the load current. It is the earth fault detection in the RCD, how it is taking place. It is always comparing the input current and output current. Say for example, line and neutral. If there is a difference between the line and neutral current, that is incoming current and then return current, if there is a difference, then the difference, if it is more than the I delta N value, that is a rated residual current, I delta N value, then it is going to trip. Usually the I delta N value is going to be very, very small. So it will be 10 milliampere, 30 milliampere, 100 milliampere or 300 milliampere. So these are the different I delta N value, rated standard I delta N value used. So this is how RCD is different from the MCB. So now let us see what happens if there is a overload condition in the circuit. I don't have the MCB here. I have only RCD. Okay, I don't have the MCB for this explanation purpose. Now I have connected the circuit and the load is connected. Now say for example the load supposed to take 5 amperes current. This is the normal operating current. Okay, but the load now takes 10 amperes of current. Okay, so this is the normal current 5 amperes, but now because of the overload, the load is taking 10 amperes of current. What will happen during this in the RCD? Here the line current for the first case 5 amperes, okay, in the normal condition, and the return current also 5 amperes. So it will nullify each other, 5 ampere minus 5 ampere, 0 amperes. So there will not be any sensing coil, sensing. So then the relay is going to be in the same condition. In the second condition, when there is a overload, that time also the line current is 10 ampere and similarly the neutral current also 10 ampere. So if you see the net result for both cases, it is going to be 0, so that the sensing coil is not going to sense any signal here and the relay is going to be in off condition itself. So what I mean, so during overload condition, the RCD is not going to open the circuit at all until otherwise the overload happens because of the wire touches the external circuit. If the current is circulating inside the circuit itself, the line and neutral current are equal, so sure it is not going to open. If the overload happens because that there is a leakage outside the body, so the line current and the neutral current difference is created, then it will open the circuit, otherwise no. And similarly during short circuit also, if there is a short circuit here, okay, again you see the current, the short circuit current, whatever the incoming current in the coil, the same amount of short circuit current is flowing in the return coil as well. So here, so that means we have a same line current and neutral current are equal in opposite direction. Again the net result will be 0, the sensing coil will not sense, and then obviously the relay is not going to open. So by this, what we can conclude, the RCD is not going to open during short circuit and overload condition until otherwise the fault happens, the current leaks to the external body. If the fault current is circulating in the circuit, when the line and neutral is having same amount of current, that for sure the RCD is not going to open the circuit. So we have seen scenarios where the MCB fails, also where the RCD fails. So it's not failing, actually it is designed for doing that work, not the other work. Okay, MCB is designed to look after the line current. If it exceeds the rated current of MCB, it will open. Here this RCD is designed to compare these two, line and neutral, whatever the current which is flowing inside and outside, it is not going to bother. If it is equal, it is not going to open. If it is different, then it is going to open. Okay, so this is the difference. So we must have both of these devices in the circuit to protect human as well as the circuit from the fault. So short circuit fault and overload fault, MCB or fuse will take care of it, and then a leakage fault, obviously RCD will take care of it. So by having these two devices in an electrical circuit, we can protect the livestock as well as the machines from the fault. So specifications, usually the RCD will have these ratings. So 30 milliamperes, 100 milliamperes and 300 milliamperes. So these two, 30 and 100 milliamperes, are mostly used for human protection. Okay, so because the human being start sensing the electrical current in the human body when it is crossing 30 milliamperes. So if you have a 30 milliampere, it will have a high sensitivity, it can protect you better, but sometime it will trip. Even the installation is becoming old, so it will trip frequently. So sometimes they are also using 100 milliampere, so that here the protection level is little lesser compared to 30 milliampere, but it will not trip frequently. Okay, so we have to think about which one you want, safety level, or what level of safety level you need. And there is 10 milliampere RCDs also available. Okay, in some specific areas the current rating should be very less, so their protection level can be 10 milliamperes also can be used. And for the installations, the machine equipments and all those things, we can have up to 300 milliamperes. So factors which would affect the trip time of the RCD is earth fault loop impedance. So I also put a video for this. Please refer that video, what is the earth fault loop impedance and how it is affecting the trip time of the RCD. So here I would like to say that earth fault loop impedance should be maintained very less, so that the trip time will be fast. And the short circuit current, obviously based upon the resistance and the supply voltage, so the short circuit current would change. So if the resistance offered is low, then the short circuit current would be very high and the trip current time will be very less. It will open the circuit very fast. So for personal protection, RCDs must trip within 40 milliseconds. As I told you earlier, for the MCB it is 100 milliseconds. For RCD it is 40 milliseconds. It is very basic because the RCDs are used to protect a human being. So it should be very fast, so that no damage will happen to the human. Obviously, the equipments also need to be safeguarded, so that it has to trip. But compared to the human body, the machines can sustain for a few more milliseconds. So 100 milliseconds for the MCB. So that's it about the type of faults and protective devices used to protect us from that particular type of faults. Hope you will understand the concepts and you enjoyed the video. Thank you for patience listening, and subscribe our channel. You will get more and more of a technical videos, and we will learn together with this channel. Thank you.